Welcome to the Advanced Higher Physics course here in St Aloysius College. Unit 1, Rotational Motion and Astrophysics. Section 1 of this course is called Kinematic Relationships, and I have split kinematic relationships up into two parts. This is part 1. So, what will you be learning in part 1 of kinematic relationships? Well, the main focus is on the equations of motion, the very same equations of motion you met at higher. However, the main difference at advanced higher is you will be expected to derive these equations of motion using calculus notation, and you'll then use them to solve problems as you would expect. Before we proceed, a word on what we are studying. This section of the course falls under the heading of mechanics. Mechanics, of course, is that branch of physics which studies the motion of bodies. Mechanics itself can be subdivided into two main parts. Kinematics, the subject of this part of the course, and kinematics seeks to describe how bodies move. It's not so much interested in why they move, it simply wishes to describe how they move, and forces are not required to do that. The other main subdivision is dynamics, and in dynamics we seek to explain why bodies move, and to do that we require to involve force. We are going to begin then by considering displacement S. If you look at the diagram, you'll see we have a particle that we are going to imagine exists at the origin of an x-axis, O. The particle is the round sand-coloured circle, and it's going to be moving to the right towards point X along a nice straight line. At first then, let's imagine that the particle moves through a displacement S to point P. There she goes. The particle has now completed a displacement S, and it has taken a time t to do so. And it's now at point P. All well and good. Now let's imagine that the particle covers an additional displacement, which we'll call delta S, during a short time, delta t. It's now reached point Q. There we are. The total time taken to reach Q is therefore t plus delta t. Now, in all the cases we deal with, the displacement S will always vary with regard to t in a well-defined way. Mathematically, we say that S is a function of t, or in symbols, S equals f of t. Now, we won't actually use this function notation very much in the advanced higher course, but it's as well that you're familiar with it. You have in fact already worked with S being a function of t when you use the displacement equals velocity times time equation in National 5. We now consider velocity v. So our particle is still moving along our x-axis from O towards x. Let's focus on that little section of its journey between P and Q. Ask yourself this question: what would the average velocity of the particle be between P and Q? Imagine the equation in your head right now. Well, the answer is that the average velocity is simply delta S divided by delta t, the small displacement between P and Q divided by the time taken, delta t. What if I asked you to consider the instantaneous velocity of the particle between P and Q? What would that be? Well, because an instantaneous velocity refers to a velocity at an instant, the size of delta t must be very, very small. How small can it be? Well, mathematically, the smallest delta t can be is that it gets so close to zero that it can't get any closer. But it can never actually become zero, of course, otherwise the equation would be undefined. So we express this tiny little delta t as the limit as delta t tends to zero of delta s over delta t. Now this is slightly clumsy notation to use, so we're going to now use the calculus notation you learned in your higher maths course. So v then becomes ds by dt. This d notation was invented for convenience, really, so that we didn't have to keep writing out the limit as delta t tends to zero all the time. So the dt represents an infinitesimally small duration of time, and consequently the ds represents an infinitesimally small displacement which results. And v, of course, is the instantaneous velocity. Finally, we come to the acceleration a. Again, our particle is moving along the line OX, and we are interested in a small section of its motion between P and Q, as before. This time, however, the particle is not moving with a uniform velocity, it is accelerating. So we're going to imagine that it has a particular velocity v1 whilst at point P, but that it's speeding up, and by the time it gets to point Q, its velocity is increased to v2. So there's clearly been a change in velocity, we'll call that delta v, and delta v, of course, equals v2 minus v1. And this change occurs during a time interval delta t. You can see the double-headed arrow at the top there represents an acceleration. In your head then, can you imagine an expression for the average acceleration of the body between P and Q? Well, as before, the average acceleration is simply the change in velocity divided by the time interval delta t. So acceleration is delta v over delta t. If I were to ask you to imagine an expression for the instantaneous acceleration, you could apply the same reasoning that we did when considering the instantaneous velocity. We would imagine that delta t is an infinitesimally small time interval, and the instantaneous acceleration then would be the limit as delta t tends to zero of delta v over delta t. Now, of course, we will again use calculus notation to say that the acceleration, that is the instantaneous acceleration, is dv by dt. Now, we would only require an instantaneous acceleration to be calculated if the acceleration were changing. Otherwise, the average acceleration describes the full picture. And you will meet occasions when the acceleration is non-uniform at advanced higher. So just to sum up, dt is the infinitesimally small duration of time, dv is the resulting infinitesimally small change in velocity which takes place during that time interval, and of course a is the instantaneous acceleration. And so we now come to the derivations of the equations of motions themselves. Firstly, an alert. you're going to be required in the Advanced Higher course to know these derivations by heart. The only good way of doing this is simply to practice deriving them yourself from start to finish regularly. When you first do this, you'll make lots and lots of mistakes and you'll forget things. That's perfectly normal. Everyone is the same. But with practice, you will gradually have them memorized, and after that, it's plain sailing. The first equation of motion's derivation. Well, firstly, one or two points about mastering derivations in advanced higher physics. Before you begin any derivation, you must be very clear in your head about what it is you are trying to derive. You need to have a clear sense of what the final equation actually is. Very often this will be given to you in a question, and therefore it's clear. But it's essential that you know where you're going before you start the journey. The first equation of motion then, in order to derive it, we need to know what the first equation of motion is. I suspect you can imagine it right now. There it is. V equals u plus at. So we have our endpoint. We have our target equation. The second thing that's essential in any derivation is to know what your starting point is. Now, there's no way around this. You've simply got to memorize the starting point. So, in this particular case, our starting point will be A equals dv by dt. Now, if we look at our starting point and we look at our finishing point, we can see some connections. The target equation has v on the left-hand side, it's the subject of the equation, and it has t on the right-hand side. Our starting equation also has t and v and a involved. So let's take a first step towards the target equation by rearranging our starting point to get v on the left-hand side, because that's going to be required in the end anyway. There we are. So we rearrange for dv equals a dt. Next, we should notice that the target equation has no differential terms, no dv's or dt's. It has finite terms, v, u, a, and t. So we're going to have to move from having these differential terms, dv and dt, into finite terms. And the way that we do that is by integrating. So we're going to have to integrate both sides of this equation. And here's how we do it. We integrate the left-hand side between limits u, the initial velocity, as the lower limit, and v, the final velocity, as the higher limit. So that's our integral of dv between u and v. On the right-hand side, we conventionally integrate our dt expression between limits of 0 and t. Okay, so let's do the integration, and I'm sure you will find this very straightforward given your higher maths knowledge. Well, when you integrate dv, you get v, and the limits are outside the square brackets. When we integrate the right-hand side, we should notice that a is a constant and is therefore not subject to integration. A is not time dependent, so it comes out of the integration, and we integrate dt and we get t with its limits. Let's expand these brackets out, and we'll get v minus u equals a into t minus 0. Tidying that up, we get v is u plus at, the first equation of motion. Now I can hear you say, I enjoyed that. Let's do another one. Well, let's. So the second equation of motion. Again, before you begin the derivation, you must be very clear on what your target equation is, the end point. I'm sure you can all remember the second equation of motion. It is, of course, s equals ut plus a half at squared. What is our starting point in this derivation? You've simply got to memorize this, and here it is. We begin with v equals ds by dt. Now, if we compare our starting point and our end point, we want to have s on the left-hand side. So let's take our first line of reasoning forward and rearrange for ds equals v dt. Well, that's a step in the right direction. We've got s on the left-hand side, and we've got t on the right-hand side. We've still got the differential terms to deal with. And the other thing we should notice at this point is that there's a v on the right-hand side up at the top there, but there's no v in the final equation. So we're going to have to substitute for v at some point. Anyway, let's get rid of the differentials by integrating again. We integrate both sides. The conventional limits for s are from 0 to some displacement s, and again for t from 0 to some time t. Now on the right hand side at this point, v as it stood did not have a time explicitly shown in it. So we're going to replace the v by substituting for v equals u plus at, the first equation of motion, of course. So we replace our v by u plus at. That then gives us a function of t to integrate. We now apply the normal rules of integration. So on the left-hand side, we have s between the limits. And on the right-hand side, we apply the normal rules of integration. So integrating u with respect to t gives us ut. And integrating at with respect to t, we raise the power by 1 to give us t squared. And we divide by that new power to give us a half at squared. Again, between the usual limits. Let's work that out. So s minus 0 is equal to ut plus half at squared minus 0. Tidy that up, and we have s equals ut plus a half at squared, the second equation of motion. I'm enjoying this, I hear you say. Give me more. Okay, I have more for you. Let's derive the third equation of motion. Do you remember what it is? Of course you do. V squared equals u squared plus 2as. This time we're going to take a slightly different approach. We're basically going to use equations 1 and 2 from the equations of motion and combine them with a little bit of mathematics. Well, we begin with equation 1. V equals u plus at. That's our starting point. That's our first equation of motion, in fact. Now, comparing that with the target equation, we have a v on the left-hand side, so that's good. We've got a u on the right-hand side, that's also good. And a is also on the right-hand side, so some elements of the final equation are already in place. However, there is no time in the final equation, so we're going to have to eliminate t. And also, the v and u terms seem to have been squared. Well, let's deal with that squaring issue first. So what we're now going to do is square both sides. So v squared equals u plus at all squared. And I'm sure from maths you'll know how to expand out the brackets when you've got a squared term in brackets. So we've got v squared equals u squared plus 2uat plus a squared t squared. Okay, we're getting close, but we still have that t term we need to get sorted out. Well, here's what we're going to do. We spot that in the last two terms on the right, there is a common factor. Can you see what it is? It's a. So in fact, we're going to take out a common factor of 2a, like this. Have a look at that expression and just be assured that it follows from the line above. I'm sure you'll agree it does. We've essentially manipulated the algebra here to get that square bracketed term. Do you recognise what is in the square brackets? It's ut plus a half at squared, which of course is simply s. It's our second equation of motion, and that takes us to v squared equals u squared plus 2as, the third equation of motion. We're going to add in one short extra derivation that you should know, and this is a very simple one. We simply begin with s equals vt. Again, it's a uniform acceleration, but for a uniform acceleration you may recall from higher this equation, v equals u plus v over 2. It only works for uniform accelerations, and you may not have actually used it very much at higher, but you have met it. Well, if we substitute that in for v, we get s equals u plus v over 2 times t. And that is our fourth equation of motion. Well, scholars, that brings us to the end of Kinematic Relationships Part 1. I hope you've found it interesting. The most important thing you must do before moving on is to make sure that you can use everything you've learned to solve problems with confidence. And you'll be given instructions on these as we go along. Once you've done that, you'll be ready to move on to Kinematic Relationships Part 2. Good luck and see you soon.